He will talk about mosaics from Mars.
Hi, good afternoon. You may have seen the big mosaic on the side here. You talk a little bit about how we make things like this in the context of the Mars mission to JPL. I should say that these results are not part of the Provide project per se. I'm on the advisory board for Provide, which is why I'm here to help help advise the project on where it should go. So how do we experience Mars? Well, this is how the rover sees it. You know, little 1K by 1K pictures that really don't make any sense on their own, or not much anyway. What we want to see is something like this. So, you know, mosaics provide a much cleaner, more cohesive view of the surface. So you can actually understand the environment surrounding the rover, and in context. You know, so you can see. Let's see. There we go. So you can see the you know, the rover tracks going off in the distance. You can see the mountain here in the background, and you can see how everything relates to each other, which you can't see, you know, on the individual pictures. So panoramas go back a long way in history. This is a example from the Panoramic Museum in Salzburg, which I hope to visit this weekend, from 1829, and you know, they're a great way to see the entire surroundings of your environment. Moving a little bit farther, and or a little less in the past, we have the mosaics from well, not really mosaics, but panoramas from Viking Lander. The camera was actually a panoramic camera there. It didn't take individual frames, but it took a panorama directly. But these are just examples from 1976 Lander, Viking Lander 1 and 2. Moving a little more recently is 1997 Mars Pathfinder, as Gerhard mentioned. We have the this is actually one mosaic. I had to cut it so you can see it, because the one problem with panoramas is they're very wide, and so they don't show up well on screens. Even more recently, we have the Mars exploration rover rovers, Spirit and Opportunity. Spirit died several years ago after a long life. Opportunity is still running after almost 12 years, almost 13. Did I get that right? Yeah. So the top is a mosaic from Spirit, showing a place called McMurdo, where it spent the winter, and very close to where it ended up at the end of its mission. And is a mosaic from Opportunity, showing the a crater that visited along the way. So a little background. I'm with the Multi-Mission Image Processing Lab at JPL. Our history goes back to the 1960s. Actually, our image processing system, called Vicar, is going to be celebrating its 50th birthday next year. And we think it's the oldest continuously used image processing system in the world. We can't prove this, but we think so. And you know, we still use it today. Obviously, it looks very little like it did 50 years ago. It's like, you know, there's an old joke about George Washington's axe. It's like, this is the axe he used to cut down the famous cherry tree. Well, then the next owner replaced the axe head because it was getting worn, and then the next owner after that replaced the handle because it was getting worn. But it's the same axe. Anyway, we provide instrument data processing and services for many different missions, both science and operations, and not just images. We also do other kinds of instrument data. We support most of the JPL missions: Voyager, Cassini, Magellan, Galileo. But I'm going to focus on the Mars missions because that's where I work. So on the Mars missions, our responsibilities are to reconstruct the instrument data from telemetry. This is creating the first order data product, which we call EDRs, and then systematic creation of derived products, which we call RDRs from that. There's over 24 distinct products we make for every stereo pair of images that comes down. Things like, XYZ maps, slope maps, these kind of things. A lot of special products for operations science, and also public outreach is a big part of what we do. And we're in the critical path of operations because the products we make are required for planning the next day's activities of the rover, especially the 3D terrains. On MSL, there are 17 cameras, and we process data from all of them. There's PAS cams, front and back, hazard avoidance cameras. There's an arm camera here. Otherwise, all the cameras on the mast. The nav cams are black and white. Mast cams are the color cameras, and the cam is a special camera for the laser instrument. So here's an example of some Navcam mosaics that we make. This is a cylindrical projection. It's the most common projection. It's the same as what we have on the wall over here. But it shows you a good, it's like the panorama in the museum. It's the nice way of seeing your terrain all the way around you. Polar projection is different. It's like you're looking from above with a fisheye lens, so you can see all the way from the ground, from the nadir out to the horizon, all the way around. A vertical projection. This is a quick overhead view. It does not require stereo, but it's like you're looking up from up above. But you notice the rocks get laid over, and so does the rover. It gets distorted because we're not looking at the 3D. And I'll talk about that a little bit more. This is the orthorectoid projection, which does use stereo, and so is a true overhead view. The rocks are proper, and there's shadows behind them because we don't know what's back there because we can't see behind the rock. And there's also stereo view. If you had red blue glasses, you could see this, but the point is you can make panoramic mosaics in stereo as well. So how do we make these things? Well, basically, a mosaic is a single large image that is made by combining many smaller images. The problem is these small images are not all taken from the same position, and so you have to transform them so they look like they came from a unified whole. And we accomplish this by taking each frame, projecting it down to the surface, and then look at that surface from a different point of view. And I have slides that go through this process. We do require that images have a calibrated camera model. Camera model translates between the line sample coordinate in the image and the XYZ in the real world. So it tells you for any given point where does it project into the image, and vice versa. And we also need to know the pointing of each in the image. We have telemetry from the camera mount that tells us what our azimuth and elevation is for each of the frames. Some of the challenges are parallax. I'll talk about that. Imprecise pointing knowledge, where we know what these positions are, but not very precisely, and radiometric matching, which is just getting the brightnesses to match. So parallax. Parallax happens when you look at a 3D scene from two different points of view. If you hold your finger in front of your face and close one eye and the other, your finger moves against the background, which doesn't move. This is very important because this is the basis of stereo vision. That's why stereo 3D processing works. However, it's a big problem for mosaics because when your camera moves, the scene changes. And this causes problems with occlusion, where from one point of view the background is covered, but from another point of view you can see behind it. And also, for something very close by, you might see different sides of the same object. So this one camera might see one side of the rock, and the other camera might see the other side of a rock. That's all great if you're doing stereo, but if you're trying to do a mosaic from a unified point of view, that makes it hard. This is a selfie from MSL, taken by the arm camera. So it holds the arm camera out in front of itself and takes, I think it's about 20, 30 pictures, something like that. But this is a super simple mosaic because the arm has enough degrees of freedom that it can keep the camera in the same position entrance pupil of the camera in the same position as it takes all the frames of the mosaic. So putting it together in mosaic is a snap because there's no parallax, and this is super simple to make. It's also very dramatic. Of course, the arm gets cut off because you can't actually take a picture of the arm from the arm, but oh well. However, for the mass cameras, you have you don't have that much degree of freedom. The camera, if a point camera, this is this left and right stereo pair. If it's here, if it's pointing this way, it's here. But when you change the angle at which you're looking, you also are changing the position because the cameras rotate around on a mass that's turning. So that means that the cameras are actually physically moving and not just rotating around their entrance pupil. And then it introduces parallax. So perfect correction of parallax is not possible. There are several different approaches to deal with it. One is an orthorectify projection. I showed you that picture. Basically, you use the 3D information of the scene in order to put all the pixels in the right place and therefore eliminate parallax. In principle, the seams can be perfect if your XYZ data is perfect, but of course it never is. This also creates holes or gores in the images, and that can be a bit of a problem for public outreach because people really will come and ask, why are there holes in the image? What are you hiding? Anyway, I'm not kidding, they do. But what we generally do is a surface model-based projection. This ensures there are no holes in the image. You do not need stereo information, but deviations from the surface model will create errors due to parallax. And I'll show this in a second. The other method is image warping, where you actually pretend the image is on a rubber sheet, you stretch it or compress it and do various things to force the edges to match. This creates an illusion of no seams and can create really pretty pictures, but it really kind of messes up the scientific interpretation of the pictures because suddenly you've transformed them in some way that doesn't make sense. Here's an example of parallax. This is 2 image frames taken by the McMurdo rover, and if we set the surface model on the ground, we get a nice, perfect, seamless ground here. But we have a seam on the rover deck. If we set the surface model to where the deck is, that's perfectly seamless, but we have a seam on the ground. So you can see from these 2 images that because of occlusions and stuff, if you matched both this and both the solar panels and the ground, something would have to give. You'd either have to cover up a lot of ground here and lose the ground, or you'd have to create a hole and move this down, and there'd be a gap here. And that's the fundamental challenge of parallax. So now I'm going to go through the mosaic process graphically and hopefully better explain the process. So let's say we have a 3D scene. There's 3 objects. They're all sitting on the ground. Now we put 2 of these cameras in, and it's the same from a couple of views ago. As you change the direction, the camera moves. So there's one camera here, and the other one's back here. They're looking out at the scene. Take the camera away and put, this is the image frame. This is how these images project on the image frame. If we look at those as images, that's what we look like. So, given this scene, here's our 2 images. Okay. If we just put these together in a naive way, we get this. It's like, okay, yeah, it sort of matches here at the corner, but you can tell nothing is anywhere close to where it needs to be. So now we take those same 2 images and project them from the camera back down onto a flat plane. So this is there's no longer any 3D objects here. This is a flat surface. And you ray trace each of the corners of these objects down, and they all project like this onto that flat plane. So then you look at this from the same point of view, like halfway in between these cameras, and you get that. So you can see this is the seam line, and you can see that it matches quite well. So now, parallax. If you put some tall, and you know, when everything is very close to the surface model, there is no parallax, and everything works great. Now we put some tall objects in the scene. Here's the frames projected, same thing, and the original frames. Now, when you do the mosaic in the same process, it looks like this. It's close, but it's not perfect. If you zoom in up here, you see how much this is misregistered here. And if you looked at the base, which is not on this image, but the base is perfectly registered, and up here it's not. And that's due to parallax. The top of this is not on the surface model, and so there's distortion. So how do we fix these problems? We can attempt to minimize the impact of parallax errors. They're fundamentally unfixable, but we can do things that reduce the visual impact so that you don't see them as much. We can also actually fix the pointing knowledge error. So if the camera was actually pointed here and we thought it was pointed there, we can fix that and say, okay, point there instead. When we do pointing correction, there's a couple important principles. Most important one is we want to maintain our scientific integrity of the results. I mean, this is not, the purpose of this is not to make pretty pictures, although we like making pretty pictures. The purpose of this is to make things that are useful for driving the rover, interpreting the terrain, and scientific uses. So it's very important we can maintain the traceability of results. We know, given a pixel on the mosaic, we can mathematically tell you where that pixel came from in the source images. By the same token, we don't want to do unconstrained warping. You know, we want to treat the image as a single entity. We don't want to do the rubber sheeting thing because that makes it very hard to maintain this traceability. So essentially, we're repointing the camera as a whole, not the individual pixels. We want to make use of a priori metadata. So this is the information the rover tells us about the pointing of the images. This ensures the results do not go out to lunch. There are stitching programs out there, Microsoft ICE is an example, that will take just random images and put them together into Mosaic. And it works beautifully. It gives you great looking results. You know, if you have a bunch of tourist images of Stephen's Dome, and it'll put them all together into great panorama, and everything's awesome. But we've actually seen cases where frames are swapped, where if you have frames, you know, A, B, C, and D, it'll put them in the order A, C, D, B, or something. And when you look at the result, it does such a good job of seam blending, you can't tell it's wrong. Because, you know, unlike images of Stephen's Dome, where you can see that doesn't look like a building, you know, it's Mars. You don't know what it's supposed to look like. So if there's, you know, sand or rock out of place, you wouldn't know that. So using a priori metadata that says, yeah, we're pointed this way is very important. So you know that, yeah, we really are pointing that way. And if I can move a little bit, that's fine, because there's errors. But if I say suddenly I should be pointing over here, that's not good. We also don't want to blend the seams. That can create fuzzy areas and artifacts around the seams, which could lead to misinterpretation of the data. We'd rather have a sharp cut line that, you know, if you can see the cut line, you know that it's an artifact as opposed to something actually in the data. We do try to minimize visible seams, however. It's not always possible to parallax, but like I said, we want hard edge seams. But it's okay to reorder images and do things like that to hide seams in less visible locations. For example, you don't want the seam to split a rock. You know, if you reorder the images, and the seam will be on the side of the rock and won't be as visible. Okay, so the correction process in a nutshell. First, we'll reorder the images, try to put the seams in least visible places. And we'll gather tie points. Tie points are when you look at two images that overlap, it says this feature on this image is the same as this feature on this image. It gives you the coordinates of these two and says that they match. There's automated collection of tie points, but there's also a manual assist where you can go in and fix problems with them. Then there's a bundle adjustment process, which basically says, okay, if these two points are the same in the mosaic, they should end up on top of each other. And if they don't, if they end up next to each other, that's an error. And so it will adjust the pointing to minimize this error. And it's called a bundle adjustment process. And you think of it, the tie points are little springs that pull the image in one way or the other. And the farther off you are from where it's supposed to be, the harder the spring pulls. And so it does a global, simultaneous global solution of all the pointing parameters. The parameters we adjust the pointing, the actual azimuth and elevation, or arm joint angles. There's also the surface model position and tilt, so we can actually tilt the surface. And sometimes we don't do this much, but we can also do rover position and orientation adjustment if you actually take frames from two different locations. We then take these results, apply them to the mosaic, and rinse and repeat as necessary. So here's some examples. This is a post-drive Navcam from MSL. If we zoom in on a portion of it, this is the raw image. You see this, there's a seam here and there's a seam here. There's the same area after correction where the seam has gone away due to the pointing adjustment. Here's another example. This is the arm camera on one of the MERs, probably Opportunity. Oh, definitely Opportunity from the Sol. You can see here, this is actually 4 pictures, but you can see a bad seam across here in the center, and over here it's all gone away, and you got a nice continuous mosaic. Here's another example. This is a multi-instrument combination. This is the MI, the arm camera versus the pan cam background. So here you can see this is actually going off the edge of where the rock is in the nav cam, and once it's corrected, it all looks right, and you can see little features that extend across the boundaries. This is an example of a navcam mastcam combination where you have the science camera taking these frames on the background of the navigation camera. You see the difference in size. Here's one frame. This is actually 5 mastcam frames. And here's the size of the navcam. So this is basically 3 navcam frames taking up this whole area. If we zoom in, this is the uncorrected result. And you can see there's a lot of, it really doesn't match very well at all. Corrected result here, now you can see all these rocks are continuously flow across the boundaries. So that takes us to the Gigapan over here. This is the largest surface mosaic made from Mars to date. It's about 850 images, and I don't remember the pixels. I think it's like 80,000 by 20,000-ish, something like that. And say pan the webcam over. Gerhard and his crew had this printed out on a nice fabric print over here. As big as this is, and you can see it takes the entire room, that is not showing every pixel. And it's probably at least half or maybe quarter res of what the actual full resolution is. So here's an example. This is the entire mosaic up here. We take just this little tiny spot and blow it up. It looks like this. Okay. Take just that little tiny spot and blow it up. It looks like this. This is about full res. And we find a little bird. It's my favorite artifact, or not artifact, but There's a name for it. I forget the name.
Anthropomorphism.
There's another name, but that'll work. Yeah. It's not really a bird on Mars, but it sure looks like it. But anyway, you know, if you look, you see all the detail on the bird here. You can't even see there's a bird in the full scale here. So then, now let's take this and apply it to our next mission. Our next mission is the InSight lander. It's scheduled to launch next year, and early next year, and land in, I believe, September or October. It has two primary instruments. There's a seismometer contributed by the French, and a heat probe contributed by the Germans that will dig down. I think it's 10 meters down, and has temperature sensors all along the cable. These instruments are deployed by use of the arm that actually picks them up off the deck and puts them on the ground. And the whole thing is, the lander is a derivative of the Phoenix lander from 2007. There's only two cameras on this whole mission. One is a single non-stereo HazCam, which is mounted right under the deck here. And the other is the camera on the arm. That raises a big challenge of how do you do stereo with one camera? Well, the answer is that you can move the camera. So if you take a picture here and move the camera over a little bit, take another picture, you get a stereo offset, and you can do 3D ranging. And so that's the basis of what we do to characterize the workspace here in order to tell where is it safe to put the instruments. So, yeah, talk about some of this. Stereo is a particular challenge because of the arm motion. You can have a lot more inaccuracies. Stereo ranging is very sensitive to the baseline, the distance between the cameras. On a mass camera, it's fixed, so you know what it always is on the rovers. Here, you know, you're on the end of an arm that's doing this, and you know, it moves around and eventually settles, and moves over here and eventually settles. There's a lot of errors there. So we essentially have to take these same pointing correction techniques that we use for mosaics and apply them to the images before we even do the stereo analysis. So mosaics are challenging too. By the same token, we don't know very well where the camera is, so we have much higher uncertainties in position. And also, we have a moving arm, so you have a lot more parallax issues. I mean, hugely more, because you're not just moving around a little area like this, you're moving, you know, like this. That's somewhat mitigated by the fact that we hope to land in very flat terrain. If we don't, we have some problems with deployment of the instruments. But the landing site people will say, yes, it's going to be very flat, so we hope, we hope they're right. So here's some examples from the test bed at JPL. And so this is a cylindrical mosaic of the workspace taken by the arm camera. I have to say this is all uncalibrated color. We don't have the color correction parameters in yet. So it's like 3 different tiers and 1, 2, 3, about 10 or 11 across. One of the interesting features of this camera is that the way it's mounted, you always see the end of the arm because it's mounted right under the arm, so you'll always see the end of the arm in every picture. So we have to take that out of every picture, and thus the over here, that's what this shape is. That's masking off the arm. So you have to do a lot more overlap than you would normally. So here's an overhead vertical view of the same workspace. So this is like you're looking at it from above, and that's really a much better view when you're trying to deploy the instruments, because the instrument is the same size no matter where it is in this terrain. An orthorectified view, the same thing. Let me correct you. The orthorectified is the best, better than the vertical, but for the same reasons. It's the true overhead view. Here's an example of the XYZ grid overlaid on the vertical mosaic. So you can see these lines are lines of constant X or Y, and the blue is contour lines in Z. So these are height contours. There's actually a hill we built over here and over here also. This is an overlay of a reachability map. So this tells you where the arm can actually reach the deploying instrument. So in the blue area is good. I don't remember which instrument it's for, probably the seismometer. And then if you put it right here on the edge, the legs will extend out this far. And I think, pretty sure this is a seismometer, in which case this would be how far the windshield that goes on top of it would extend. Here's a deck mosaic, which is even more challenging because of parallax. It's actually, turning and looking back at the deck. And it is really hard to do these because you're very close and you have an awful lot of things sticking up. So you see here, for example, this little cylinder is split. I don't know if you can see that from back there, but that's a parallax issue. We make sure that we take this in a single frame so that we don't have to split it for parallax reasons. So we've done some tuning of the sequence to make sure that we don't split the important hardware, or that the seams actually appear on the deck and say right down the middle of where you want to see it. Here's some other examples of the deployment mosaics. This is showing the tether, making sure the tether is laying where you want it to be, both across the deck and also on the ground. So how can you see these mosaics? Well, most of them are delivered to the Planetary Data System PDS archive. We have a tool called Mars Viewer that will show them for the MER, MSL, and Phoenix missions. Actually, Phoenix doesn't show mosaics, sorry. There's a website, PDS-imaging, jpl.nasa.gov. It's like Mars Viewer. The MSL corrected Navcam mosaics are also shown here, usually before they appear in PDS. This is every time we drive, we make a mosaic and correct it and clean it up and post it here. And then the full res Gigapan is available here. And you have interactive viewers that allow you to zoom into it and see various features, which is kind of entertaining. So I think that's it.